We are going to continue with our probability. And we are going to talk about what is called the conditional probability. So this is going to be one that we didn't cover in statistics. So those of you that took statistics, this is a different probability formula that we will talk about. And what it is saying is the probability of an event given another event occurs. So the way it's usually written is like probability of A/B. And then the second one is the one that is the second occurred. So it must occur to have the other one occur. So in this case, if A is an adult has lung cancer and B is an adult is a heavy smoker, we can find the probability of A/B, which is going to be the probability of an adult having lung cancer, given that they are a heavy smoker. That second piece of being a heavy smoker clearly is going to have an impact on the fact of you getting lung cancer, right? We know that smoking increases your risk for lung cancer versus just never touching anything like that. So when you want to find a probability like that, there's a formula we're going to follow. And you're always going to start with the intersection of the two probabilities. And then it's going to be divided by the probability of that second piece, that given piece. So if it's A/B, it's the intersection of A and B over the probability of B. Or if it was B/A, it's their intersection divided by the probability of A. A lot of times for problems like this, you're going to have a table so that these are easily found probabilities. So for the first 9 examples, we're going to use this table. So if you guys want to copy that table down, the columns are the values A, B, C, and D. And then the rows are E and F. If you sum all the totals of your columns, you will get 1. If you sum the totals of your rows, you will get 1. If we want to find the probability of the value C, all I have to do is find C. C is a column, and I look for the total for C is 0.36. So if I just want, looking at this information, the probability that I am C, whatever C stands for, is 0.36. 36% of this table is C. I want to find the probability of F. Well, F is a row, so I'm going to follow F's row all the way to its total, and that is 0.8. So 80% of the table is in F. The third one says what's the probability of A intersect F. So where does A overlap with F? So A is this column, F is the row, and they intersect here at 0.05. I want to do another intersection, C and E. So C is the third column, E is the first row. So C intersects E right here at 0.06. And now we're going to go into our conditional probabilities. So it wants us to find the probability of A given that F has occurred. So the way we do these, you're going to find, so the probability of their intersection is going to go on top, and then the probability of the second letter is going to go on the bottom. So A intersects F. So we're going to look for A intersect F, and we're going to put that over the probability of F. So A intersects F, we already have that as 0.05. And we already have the probability of F listed as 0.8. So I'm going to take 0.05 and divide by 0.8. And when you do that, you get 0.0625. The next one, probability of F, given that A has occurred. So again, we're going to look for their intersection, but then we're going to divide this one by the probability of A. So what's happening here is I'm literally just using column A. When it says find the probability of F given A, it's saying only look at A and tell me the probability of getting F when you're looking at A. Well, because look, the probability I get F is 0.05 out of 0.07. That's exactly what I have here. F intersects A is 0.05. Probability of A is 0.07. So these are just saying, instead of looking at the whole, I want to look at a specific column or a specific row, and I want to find the probability of getting a letter within that column or row. So let's see, if we take 0.05 divided by 0.07, that's going to be about 0.714. So if I'm only working in column A, I have a 71, about a little over 71% chance of picking F over E. Does that make sense? So you can default to the formula, or you can think about it in terms of the column or row. So if I want to kind of do that same thing here with the next one. So I want the probability of D given that I'm only looking at E. So I'm only looking at E. So I'm only using that top row. Well, the probability I get D is 0.04 out of a total of 0.2. And that is 0.04 is the intersection of E and D over the probability of E, 0.2. 0.04 out of 0.2 is 0.20 or 20%. So I want to do the next one in that same setup. Probability of E, given I'm only working with B. So I'm only working with this column. Well, E happens 0.08 out of 0.18. 0.08 is the intersection of E and B. 0.18 is the total probability of B. And when you divide those, this is about 0.44. I think it keeps repeating. And then the last one here is saying the probability of C, given that I'm only looking at C. So if I'm only looking at C, the only thing I can pull is C. So the probability of C given C is 1 whole. If I'm just going to throw this extra one here, probability of C given D. I'm just going to show you one that doesn't work. So I want to pick the probability of C, given that I'm only working with D. Okay, D is over here. C is over here. Can C happen with D? No. There is no intersection of C and D, so this is a impossible probability. So because I showed you a certainty probability, one that is 1, and the letters are exactly the same, I wanted to show you an impossible one. So if you're working with 2 columns, it will not work, or if you're comparing 2 rows, it will not work. We are now going to talk about the AND probabilities that we did talk about in statistics, with reaching into a bag and drawing something out and determining, do I put it back in? Am I not replacing? And how does that impact my probabilities? So in a bag, I have 5 red balls, 7 green, and 8 white. What I'm going to do is draw 2. I'm no longer just doing one single event. I am doing 2 events here. I want to find the probability that both are green with replacement. So the way I like to do this is I like to think about it as the first draw and the second draw. So when I reach in the bag the first time, I want to get a green. Well, there are 7 green out of, what are we at? Is that 20? Add those all together? Yes. So I reach in the bag, probably to get a green is 7 out of 20. Whatever I grab, I'm putting back in the bag. That is what with replacement means. I put it back in the bag. So I still have all 20 in that bag. So the probability I'd go back in and grab a green again has not changed. So 7 out of 20 times 7 out of 20, that's going to give me 49 out of 400. You could stop there. Or if you wanted the decimal equivalent, 0.1225. All right, the next question says probability that neither of them are green. Well, if 7 out of the 20 are green, 13 out of the 20 are not green. And I am again replacing. So my probability is not going to change. It's going to stay 13 out of 20. 13 times 13 is 169 out of 400. And if I turn that into a decimal, just divide 169 by 400, 0.4225. Now I'm going to change the directions. I want both to be green, but now I am not replacing. So my initial probability is still that 7 out of 20. I know that when I reach in that bag initially, there's 7 green out of 20 colored balls. However, I'm going to keep that 1 green out of the bag. So how many greens are there now in the bag? Out of how many total? 6 out of 19, exactly. So that is the difference. With replacement, probability does not change. If I am no longer replacing, I have to subtract the one that I have taken out. So this now becomes 42 out of, what's that, 380. And when I divide those, I think it's 0.1105. All right, so if I don't want either of them to be green, and this time I'm no longer replacing, I'm going to go back to the second one we did here. 13 out of 20 is what I started with. But one of those that I took out is not green, and I'm not going to replace it. So now I drop down to 12 out of 19. And that's going to give me another 12, 156 out of 380. Or 0.4105. This one says, an automobile manufacturer produces 30% of its cars at plant A. If 5% of the cars manufactured at plant A have a defective emission control device, what is the probability that one of its manufactured cars was manufactured at plant A and has a defective emission control device? So here's what we have. Probability at A is 0.37, 37%. If 5% of the cars manufactured at plant A, okay, so probability of a defect is 5%, 0.05. This one wants us to find the probability that it was produced at A and is defective. I totally misspelled defective. And implies multiplication. So probability of A times the probability of B. I'm going to take the 0.37 times the 0.05, and I will get 0.0185. We are going to have a box that now has 3 red and 5 green balls. If 2 of them are going to be drawn without replacing, we want to find the probability the second is green. I have 3 red, 5 green. What is the probability the second is green? All right, the way my brain thinks about this is I could draw a red and then a green, because it's just telling me the second one has to be green. Or I can choose a green and then a second green. So if I work with the first one, there's 3 red out of a total of 8. Once I've drawn that first one out, I'm no longer replacing it. So I now only have 7 balls in the box, of which 5 are green. So the probability I then get a green is 5 out of 7. I'm going to do the same thing for the green and green. So reach in the box the first time, 5 out of 8 are green. Once I've pulled that one out, there's now 4 of the 7 remaining that are green. So this first one, we've got 15 out of 56. And the second one is 20 out of 56. And then all I have to do is OR implies that I add them together. So 35 out of 56 is going to give me 0.625. All right, so next we have a tree diagram here. And at the start, we can choose between M or N. That is our first choice. The second choice is then R or S. So I can choose M and then choose R or S. I can choose N and then choose R or S. First one says the probability of M and S. So I want both M and S to occur. So I can take the probability of M and times by the probability of S. Now, how do I know what their probabilities are? Well, that is the number on the line before the letter. So the probability of M is 0.3. The probability of S off of M is 0.8. So that is 0.24. So this path here is 0.24. Now I can find the probability of every single path here. So if I did M and then R, 0.3 times 0.2 is going to give me 0.06. 0.7 times 0.4 is going to give me 0.28. And then 0.7 times 0.6 is going to give me 0.42. And if you look at all of these, they should total 1. Now I needed to do that in order to answer the second part here. Probability that I get an R. Well, I get an R up here. And I get an R right here. So if I choose M then R, I get an R. If I choose N then R, I get an R. So those two combined make a total of 0.34, or 34% of our results end with an R. Okay, sometimes it helps us to draw a tree diagram to help us in solving these. A certain state allows a person 3 tries to pass the written portion of the test to obtain a driver's license. If a person fails the test, he or she may retake the test a week later. If a person fails the written portion 3 times, they then must wait a year from the date of the third before they can try again. From past records, 80% pass the test on the first attempt. Okay, so here's my start. You can either pass or you can fail. And I'm going to actually put this up a little higher. Because if I pass, I'm done. So 80% pass, so 0.80 pass, 0.20 are going to fail. From past records, 80% pass the test on the first attempt. 20% then pass on the second attempt. So I'm going to make, in order to take a second attempt, you have to have failed the first one. So I'm only going to draw off of that first F. So you can either pass or fail there. 20% of those taking a second time pass, meaning 80% will fail. And then only 15% pass the test on the third attempt. So if I needed to make a third attempt, I had to fail the first and second attempt. Pass, fail. 15% or 0.15 pass. And that's going to be 0.85 are going to fail. All right, so I'm going to kind of work my way through here. Passing on the first attempt is 0.80. We've got that. If you fail first and then pass, so that's following this path here, fail, then pass, I'm going to multiply those two together and get 0.04. If I follow the next path down, fail, fail, pass, I have to multiply 0.2 times 0.8 times 0.15. 0.024. And then my last group fails all 3 attempts. So 0.2 times 0.8 times 0.85, 0.136. And again, if I add all of those numbers, I should reach a sum of 1. Our first question says, what's the probability of passing the written portion of the driver's test on the first or second attempt? Well, probability to pass time is 0.80. The second time pass is 0.04, or implies I'm going to add those two together. So 84% are going to pass within 1 or 2 attempts. B says, what's the probability of failing on the first and second, but then passing? Well, that's this green path I took. Fail, fail, pass was 0.024. So only about 2.4% are going to pass on their third attempt. And then C, what's the probability they'll have to wait an entire year after failing all 3 attempts? 0.136 or 13.6%. Failed miserably. You see how a tree diagram can help with situations like this where we are making multiple attempts or multiple decisions. Okay, so now we're going to talk about what is called independent and dependent. So independent are tasks that are separate or another way to think about it is the probability of one does not impact the other. So when we were doing our with replacement, that was an independent situation. Okay, if I do two completely separate events, like drawing a card and rolling a die, those are completely independent events. It doesn't matter what I roll on the die is not going to determine what card I draw out of a deck. All right, dependent is going to be when the probability of one event is impacted by another. And there is a quick test that we can perform. If the probability of A intersect B is equal to the probability of A times the probability of B, so if this creates a true statement, then I can claim independence. So basically, we just have a quick way to determine if two events are independent. I'm going to find the probability of their intersection, and I'm going to also multiply their individual probabilities together and see if I get the same result. If I get the same result, then they are considered independent. If I get different results, then they are dependent. So here's an example. In this table, we have totals from a study of males and females, and if they were left-handed or right-handed. So we sampled a total of 1,000 people at random. There were 52 left-handed females and 388 right-handed females for a total of 440 females. We had 78 left-handed males, 482 right-handed males for a total of 560 males. And then in the far right column, we have a total of 130 left-handers and 870 right-handers. So the first thing they want us to do is convert this into a probability table by dividing every entry by 1,000. Why are we dividing by 1,000? Because that is the total number of people that we worked with. So all we're doing is turning these into decimal equivalents. So this would be 0.052, 0.078, and 0.130. Next row would be 0.388, 0.482, and 0.870. 0.440, 0.560, and 1 whole. So now that we've done that, we can very easily find our probabilities. First one says, what's the probability that a person chosen at random is left-handed? Well, left-handed, total, 0.130. What's the probability a person chosen at random is a left-handed woman? Well, there were 52 out of 1,000, 0.052. Next one, what is the probability that a person is a woman given the person is left-handed? So woman or female given slash left-handed. The probability of F/L is the probability of F intersect L divided by the probability of L. So female left-handed, we said were 0.052. Probability of left-handed was 0.13. Those were the answers from B and C that we already did. So if I'm only looking at left-handed people, this gives me 0.4. So what this is telling me here is 40% of the left-handers were women. Means 60% of the left-handers were the males. This one says, what is the probability that a person is left-handed given they are a male? So left-handed / male, or in this case, not female, however you want to do that. So left and male was 0.078. And males total was 0.560. So let's see, that's going to be 0.139. So what this is telling me is about 14% of the males are left-handed, meaning the remaining 86% are right-handed, because I'm only looking at males. So 14% left-handed, 86% right-handed. So then the question becomes, are the events left-handedness and male independent? So what I need to check is the probability of left intersect male. Is that equal to the probability of left times the probability of male? Well, left intersect male was 0.078. All right, left-handed is 0.130. Male, 0.560. And if I multiply those together, I got 0.078 on the left-hand side. If I multiply the right side, 0.0728. They are not equal, and therefore they are not independent. Okay, your gender does seem to have an impact here on whether you're left or right-handed. There is a difference here. There is a relationship happening. They're not completely independent events. Says an airline has 3 independent computer chips. If the probability of failure of any one is 0.003, what is the probability that they all fail? So this is just a multiplication. So probability first fails, and the probability the second fails, and the probability the third fails. And it clearly says independent, so I can multiply each individual probability by itself. They all have that same probability of 0.003. If I multiply these, there are 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros, 2, 7. This is why things like airlines have more than one backup, because if the first one fails, they have a backup. And then if the backup fails, they have a backup to that one. And as long as their failure rates are very, very small, the fact that they would all fail in a single flight is going to be extremely unlikely. So we talked about different probabilities. We talked about our independent probabilities that we can just multiply together. We talked about our conditional probabilities where we're only working with a single column or row of our table. And that gives us our conditionals. And then we talked about that replacement without replacement, most of which was stuff from statistics, aside from checking for independence and the conditional probabilities. Those were the new ones for this class. Questions or anything else you want to see or look at?